Well, hello everyone. Welcome to our project Prime Walk to Infinity in 02. And we are the research group in Polymath REU. And today two of us, Daniel Sarnecki and Bencheng, will be presenting. Our project is advised by Professor Stephen J. Miller, tutor employed. So first of all, let us start with a simple question. Can one walk to infinity with bounded steps on real line just using primes? Well, the simple answer is no, because all we need to do is pick a prime p such that p is larger than capital M if we want a gap of length n between primes. Then the p primorial plus 2, p primorial plus 3, up to p primorial plus p are n-1 consecutive composite numbers. And where p primorial means the product of all primes less than or equal to p. Well, since primorial is defined this way, then 2, 3, and all the natural integers between 2 and p are have a cofactor with p primorial. So that's why they're composite. And well, so now what if we consider Gaussian primes instead of just the integer ring? What if we consider prime walk in primes using primes in Zi? Or Zi is a set of integers, a set of elements of the form a plus bi, where a and b are both integers. Well, the figure below shows all the Gaussian primes of norm less than 1000. We can see that the primes in the graph have a eightfold symmetry, right? And they are all tends to cluster along the near the origin. And well, this actually is a very famous and solved problem called the Gaussian Moat problem. And the Gaussian primes are, as we defined before, are prime elements of Zi, and the number of Gaussian primes in a disk of radius n has the order n squared over natural log n. And remember that the prime number theorem tells us that the number of primes between 1 and n is about n over natural log n. So there's much more primes in Zi. And well, actually, there the theorem says a mode of width 6 will exist in Zi. So this is equivalent to say that it's impossible to walk to infinity with step size 6 in Zi. And it's also widely believed that we cannot walk to infinity with any bounded step size. Well, so we start to think about if we can make it in Zi, well, can we do it in 0 to n for any integer n? Well, a simple observation would be that for negative m, the ring has only finitely many units like Zi. But if m is positive, then the ring would have infinitely many units, just like the case in 0, 2, where any power of 1 plus root 2 is the unit. So the number of prime elements would differ a lot, since any prime elements multiplied by units is also prime. Well, because the number of primes is much larger in 0 and for positive n, we conjecture that it's more possible to have a prime walk in these positive quadratic integer rings. We start with the easiest one, 0, 2. So below is some definitions of elements in this ring. The norm of an element a plus root 2b is a squared minus 2b squared. And two elements are called associates if they have the same norm. And we also define standard prime as the following forms with minimal Euclidean norm, or the square root 2 is standard prime, and any element such that its norm is a real prime congruent to 1 or 7 modulo 8 is also standard prime, and any element such that b is 0 and a is a real prime congruent to 3 or 5 modulo 8 is also standard prime in this definition. And well, using this definition, we can see that any actually primes in 0, 2 are just these standard primes with associates. And besides, we also need to notice that the primes in this definition has a fourfold symmetry. So if a plus root 2b is a prime, then a minus root 2b or minus a plus root 2b are also primes. Next, we try to compare a number of primes in a disk of radius n between Zi and 0, 2. The blue point here shows the case in 0, 2, and the red point shows the number of primes in Zi. And we can see that as n gets larger, from 10 to 60 or even larger, the gap or the difference between the number of primes also gets larger. So therefore, it means primes goes faster in 0, 2, and this fact motivates us to study prime walking in this ring. And we also use Mathematica to visualize our standard primes. Here we make each prime of the form a plus root 2b as a dot in R2. And the figure below shows all the standard primes for x, y less than or equal to 800. As we can see here, they're very dense in this region, but they're much denser along the line x minus root 2 y equals 0, which is just the asymptote of the norm function x squared minus 2y squared. So yeah, next Daniel will talk about the conjecture.
So this leads us to our conjecture, which is that there exists some finite step size k such that there exists an unbounded walk along the primes in z square root 2, where for all steps, we are getting further away from the origin, where we denote further away by using the Euclidean distance. So we have two different approaches that we are looking at. One is the random model, where we calculate the probability of integer in z square root 2 being prime. And we use this to generate walks. Then we have the exhaustive moat finding technique, which is used for Gaussian primes. So the idea for the random model is we compute an estimate for the probability a given point is prime based on its norm. Then we use this estimate to build a greedy model that approximates an average walk. This should allow us to then look at the long-term behavior of walks when it becomes too computationally expensive to generate all walks. So first we estimate the number of primes in order to calculate this probability. We consider primes in the region, the absolute value of a squared minus 2b squared is less than or equal to r squared, which is this region you could see below. The green region is for a larger constant of r, and then the blue region is for a smaller constant of r, I think 1. And then the red line that you see going through the origin is the asymptote. Now, note that this is a generalization of the disk region for Gaussian primes, but now we're using the norm of z square root 2. This necessarily means that the region is unbounded as it approaches the asymptotes, unlike the Gaussian norm region, which is just a disk, which is bounded. So we look at the prime number theorem to calculate the number of primes. For ordinary primes, the prime number theorem says that if we consider the interval from 1 to n, we'll have about n divided by log n primes. Using the connection between ordinary primes and primes in z square root 2, we are able to generalize pnt to the ring z square root 2. And this says that the number of primes in z square root 2 within the region we talked about is about this number you see right here. Now, by comparison, the prime number theorem applied to the Gaussian integers says that the number of Gaussian primes in the disk of radius r about the origin is this number you see right here. Now note that these numbers for z square root 2 and the Gaussian integers, they have the same growth. However, the region that these primes are contained in for Gaussian primes is bounded, whereas in z square root 2, it's an unbounded region with infinite area. So for a second, we look at this question of how many primes there are in a circle C of radius r in the first quadrant for Gaussian integers, because this is helpful when we're doing our walks. The Gauss circle problem helps us out here. It says that there are about pi r squared total lattice points inside a circle of radius r. This is a good enough estimate for us. We can estimate the expected value by assuming each point in an annulus between circles of radius d plus r and d minus r has about the same probability of being prime. Then we have our estimate that if C is centered d from the origin, our estimate is this number you see right here. To calculate this number, we just use the prime number theorem for Gaussian integers, and then we found a probability and then just did a simple expected value multiplication in order to get this number right here. So next, in order to make sense of the number of primes that we found, we look at the total number of integers inside this region that we were talking about for z square root 2. We would like to count families of infinite solutions that have the same magnitude as those we previously counted. That way, if we're dividing two infinite numbers, we'll still get a probability. As before, any solution or prime z that we have belongs to a family of solutions or primes that are the associates when we multiply by any power of 1 plus the square root of 2, because these maintain the norm. We can find these families of solutions by considering the equation a squared minus 2b squared equals c for each integer c with absolute value less than or equal to r squared. This theorem of Bernoulli's helps us answer this question. So if we have an integer a function defined on the integers that you see here, this quadratic form, with integer coefficients rs and t, such that s squared minus rt is not square, the number of positive integers less than n that can be expressed as f is on the order of n divided by the square root of log n. Then, to accompany this theorem, we have this little helper theorem right here that just says that if we have a solution to the equation a squared minus 2b squared equals c, then we must also have a solution to a squared minus 2b squared equals negative c. The reason why is that if we have a solution a plus b square root 2, then we multiply by 1 plus the square root of 2. This just multiplies the norm by negative 1. So as a summary of this random model right here, we're combining our two estimates and we obtain the following probability estimate, that the probability an integer in z square root of 2 with norm n is prime is on the order of 1 divided by the square root of log n. And by comparison, in z and zi, you see that the this probability is 1 divided by log n. So this differs a little bit from z square root 2.
Okay, next I will talk about our algorithm to visualize prime walks. It's by Stan Wagon's book, Computation Number Theory, and there are 4 steps altogether. The first one is to identify all primes in a disk, and then we try to find all the d neighbors for each prime. And next we will form the row network connecting all the primes and their d neighbors. And finally, we find the connected component of root 2, which is just our starting point of a prime walk. Using this algorithm, we're able to generalize these two graphs. The first one is the walk with step size root 2, and the second one is with step size equals to root 8. And we can see in this second graph that the walk tends to cluster around the asymptote, and also it tends to get closer and closer around the asymptote, which agrees our intuition and conjecture before. Next, let's look at another type of equation called Pell's equation. It's defined as x squared minus 2y squared equals 1, and a generalized Pell's equation is x squared minus 2y squared equals c for a constant c. Actually, we know that solving the integer solutions to generalized Pell's equation is just equivalent to finding all primes of norm c, since the equation is just exactly the same as the norm function. Here's lemma 1 that we proved. There is only one non-trivial solution up to associates to any generalized Pell's equation with constant c congruent to 1 or 7 modulo 8. Using this lemma, we're able to prove the next theorem, which is very interesting. It's that it's impossible to walk to infinity using primes of only finitely many norms, or equivalent to integer solutions to only finitely many generalized Pell's equations. To show this, I will show a sketch of this proof. And we start with a weaker statement. It says it's impossible to walk infinity using integer solutions to only finitely many generalized Pell's equation, including this this equation, x squared minus 2y squared equals plus or minus 1. And the way we show it is that all the integer solutions in the first octant to this equation stand for any power of 1 plus root 2 in 0, 2. And we assume that this number is equals to a plus root 2b for some ab, and then this number multiplied by 1 plus root 2 can be written as this form. And we notice that the vertical and the horizontal gap between these two numbers are both the order of b. Well, therefore, in order to fill this gap with bounded step, the number of primes between this gap should be at least have the order b. So therefore, by lemma 1, we show that we must have solutions to infinitely many Pell's equation as b tends to infinity.
Okay, and our next theorem is that it's impossible to perform a walk of bounded step size to infinity in z square root 2 if we remain some bounded distance from the asymptote that we talked about. So here's a proof sketch of this theorem. Note that we take at most x divided by the square root of 2 steps when we are x from the origin. We know this because a walk of step size square root of 2 is not possible by Ben's Moat calculation. Then the rate between the asymptote and the curve right here grows at a rate on the order of 1 divided by x. then the number of norm curves with norm plus or minus 1 mod 8 that we could possibly access at x is on the order of x divided by log x. Essentially what we're doing here is we're looking at this region, this bounded region that straddles the asymptote, and we're seeing how many possible curves can we fit inside this region. Well, then we expect 1 prime for each such curve, since the associates grow exponentially, so we expect them to outpace our walk. Thus, the number of steps grows faster than the number of options for steps, so a walk should be impossible if we stay inside this region. Here's a picture of what we're talking about here. This shaded in red region is an example of a bounded region, and then these curves here are the norm curves that we were talking about, and you see that eventually they enter the region. And here's a close-up of what we're talking about right here. We're seeing how many of these curves we can fit inside the red region. So that's the talk. We'd like to thank our mentors, Professor Stephen J. Miller, as well as Tutor and Ploy, and others from the Polymath RU for their help in this project. Thanks for listening.